Hello, chemistry students. This video is going to cover the concept of mole calculations and the different types of mole calculations. So the first thing is, it's impossible to count atoms. They're far too small. It would take us forever to count in just a glass of water how many, if we were to do it individually, how many water molecules there are. So there's a better way of counting the atoms as opposed to just physically doing it, which is impossible. We can count by weighing. So it's similar to if you were to go to a hardware store and you could see that you could buy 1,000 nails in a pound, right? So if I needed 2,000 nails, I would just weigh out 2 pounds of nails and I'd have 2,000 nails. So it's very similar to how we count atoms. We count atoms by weighing them. So by knowing their weight, we can determine the number of atoms. We also use terms like dozen to represent numbers. So if I was to tell you, oh, I have a dozen pencils, you would know that you have 12 pencils, or I have a dozen eggs, I have 12 eggs. So when we count atoms, we're going to use, because there's so many atoms in such a small space, we're going to use a term similar to a dozen to represent a number, except instead of a dozen, it's called a chemist's dozen. And instead of 12, which is not that big of a number, it's a very large number. So the chemist's dozen is referred to as the mole. So whenever you refer to mole calculations, you're thinking of a certain number of particles. And that number is 6.022 times 10 to the 23rd. And that's a really big number. It's much bigger than 12. Okay, so just to give you an example, if I owed you $1,000, that would be 10 to the 3. If I owed a million, 10 to the 6. A billion. How about a trillion? I think you get the idea of how big 10 to the 23rd is. It's almost a trillion. So it's a really big number. And one of the reasons why it's such a big number is molecules and atoms are so small. In a very small space, you can have a lot of them. And that's why we had to learn scientific notation. So now we understand that a mole is a term used to represent a number of particles. Just like a dozen represents 12, 1 mole represents 6.022 times 10 to the 23rd. This is referred to as Avogadro's number. And we're just going to use Avogadro's number as the 6.022 times 10 to the 23rd. And a lot of times you'll see it written as Na. So N with a subscript A, N representing the number of particles, A giving respect to Avogadro. So this number was defined by taking carbon-12, the isotope of carbon-12, and measuring out 12 grams of it and determining the number of atoms. So 1 mole of atoms or ions or molecules or anything that we speak of in the macroscopic world, basically 1 mole of it is 6.022 times 10 to the 23rd. And that is something that we can deal with. That is something that we can weigh out, just like that 1 pound of nails representing 1,000 nails. We can weigh out 12 grams of carbon, and that will represent 1 mole of carbon. Now, if we look on the periodic table, we see all those average atomic mass, and in the prior videos, we talked about how that was determined in AMU, which is atomic mass units. That wasn't a very meaningful size. An atomic mass unit is extremely small, 1.66 times 10 to the negative 24 grams. That's not very meaningful. So we're going to convert the AMU on the periodic table to grams. So what does 1 mole look like? Well, 1 mole of copper atoms. Well, what do? Well, we go to the periodic table and we look under copper and we see there's 2 numbers. There's 29 and the average atomic mass is 63.55. Yep. So what we're going to do is we're going to say, well, 1 mole of copper is 63.55 grams. So to get 1 mole of copper atoms, we'll just convert the unit of AMU to grams. It's very easy. So now I know if I weighed out that much copper, how many copper atoms there would be. There'd be 6.022 times 10 to the 23rd, because that's what the chemist dozen is. So 1 mole of helium, 4 grams per mole. Now it's a gas, so it expands and takes up more volume, but I think you get the idea. So every time you hear a mole, you need to think of 6.022 times 10 to the 23rd. And every time you need to figure out how much it weighs, you should look at the periodic table and look at that average atomic mass and convert the units from AMU to grams. Now, why is this useful? Well, we can use moles to the number of particles as a conversion factor, and we can flip it. So if I had a problem that's asking me how many gold atoms are in a pure gold ring of 8.83 times 10 to the negative 2 moles of gold, it's easy to solve because I know in 1 mole of anything, there's 6.022 times 10 to the 23rd. So I use my conversion factor method. I have moles of AU, gold. I make sure that in my conversion factor, the unit I'm trying to cancel out is on the bottom, and in 1 mole of anything, whether it's gold atoms or water molecules, it doesn't matter, there's 6.022 times 10 to the 23rd. I multiply these two numbers. I see that there's 3 sig figs in the problem, so my final answer has 3 sig figs, and I see that there's that many gold atoms. And it's less than 6.022 times 10 to the 23rd because 8.83 times 10 to the negative 2, right? That's moving this over 2 times, is less than 1 mole. So it makes sense. So if 1 atom of iron weighs 55.85 AMU, all you got to do is change the units to grams, and now I have 1 mole of iron atoms. It's a lot easier. Same with oxygen. Just convert AMU to grams. You can do it with molecules. So if we know that 1 molecule weighs of H2O 18.02 AMU, 1 mole is going to weigh that. And the way we got these numbers for calculating the weight of 1 molecule of H2O, we said 2 times hydrogen, 1 times oxygen, because in a water molecule, right, there's 2 hydrogens and 1 oxygen, and 2 times 1.01, again, average atomic mass, 1 times 16, so I get 2.02, 1 times 16, 2 times 1.01, add these up, I get the 18.02. But now I'm going to change the AMU, because 1 molecule is not very practical. I'm going to change that unit to grams, and I know I'll have a mole of it, which is 6.022 times 10 to the 23rd. So what's molar mass? Molar mass is the mass of 1 mole. So 32.07 grams of sulfur per 1 mole. That's a molar mass. 12.01 grams of carbon over 1 mole. These are meaningful sizes. These are amounts that we can weigh in a lab. Our scales can measure grams. So what about calcium sulfate? Now this is a little trickier. The reason why this is trickier is because they don't give you the chemical formula. So we have to now rely on our understanding of nomenclature and naming compounds. So the first thing you got to look at is, oh, this is calcium sulfate. Calcium's a metal, sulfate's a polyatomic anion. This is an ionic compound, and as soon as I know it's ionic, I need to think of my charges. So the best way to do is be like, okay, calcium, that's in group 2A, right? Alkaline earth metals, so it's 2 plus. Sulfate, oh, that's sulfur. Oh, it ends in 8, it's a non-metal 8. My teacher told me the name's derived from the non-metal, and then there's 3 or 4 oxygen. Oh, sulfur's on the 4, so there's 4 oxygen, 2 minus. Then I see that these charges would cancel each other out, and my ratio is 101, and there's calcium sulfate. And the mass is 136.14 grams per mole. Now, how did I do that? Well, I like to show students that if you write everything out, and we'll see later why I do this, it also will help you in the future when we do what's called percent composition, which is part over whole. And if I ask you, what's the percent calcium sulfate, it's a lot easier for you to do. So calcium, about that number, right? Sulfur, 32.06. 4 times 16, I add these all up, 40.08, 32.06, and then 90 or 64, sorry about that. I get that number. Now, why is this useful? Someone might say, this is a lot of work. I don't want to do this much work. Well, if I ask you, what percent is calcium in calcium sulfate? Well, that's easy. Part over whole times 100. So now you could say, oh, in calcium sulfate, the percent calcium is 40.08 over 136.14 times 100. And we could easily figure out that percent, not just for calcium, but for sulfur and oxygen. And I didn't calculate that out. Let me take a second to do that. I was kind of doing this on the fly. Let's see, 136. And you can be doing this with me to make sure I get it right. And it comes out to 29.44%. And again, you can do this for sulfur and oxygen. So now we can use these molar masses, right, that we just calculated in this previous problem. So how did I get the molar mass? Figured out the formula, tallied up the individual masses of each element represented by their subscripts, added it all up, and I see that 1 mole of calcium sulfate is 136.14 grams. Just like 1 mole of iron is 55.85. Well, really what I can do is I could use these molar masses as ratios and flip them to help me solve more mole problems. So once we understand the mole, not only does it give us the number of particles, it could also tell us the number of grams. So graphite, basically carbon, is used in pencils. How many moles of carbon are there in 0.315 grams? So we know it's grams of carbon. So what can I do? Well, I can look at my periodic table. I know I want to cancel out the unit of grams of carbon, and I look on the periodic table and I see the number for the molar mass is 12.01 grams of carbon per 1 mole of it. So if I have 0.315 grams, this is how many moles I have. And I see that this is 3 sig figs. This leading 0 doesn't count. These leadings don't count, so this is 3 sig figs. And if you want, you could have put this in scientific notation. There's no need, but if you want, you could have written it out like that. So it's very useful. Here's another example. How many grams of sulfur are in 2.78 moles of sulfur? So in the previous problem, we went from grams to moles. Well, molar mass allows us to do that because it's moles per gram. Well, if I have moles, I can get grams, right? So 2.78 moles of sulfur. So I need the molar mass of sulfur. That's easy. Look at the periodic table. I need to get rid of moles. So 1 mole of sulfur, I look on the periodic table, is 32.06 grams. I multiply it, I get 3 sig figs. And that makes sense, right? If I have almost 3 moles of sulfur, I'm going to almost have 3 times of the molar mass, 32.06, right? This is almost 90, so it's almost 3 times. What about for molecules? Can I do it? Yeah, I just have to figure out the molar mass. So nitrogen's 14 roughly. The 2 oxygen each are 16, so that's 32. 32 plus 14 is 46. All right, so I have 1.18 grams of NO2, and I want moles of NO2. Well, 1 mole of it is 46.01 grams. The grams cancel, I'm left with moles. What if I want to know from grams to the number of molecules? Now, this is there's an extra step here, right? Because from grams, we just said I could use molar mass, grams per mole to get moles. But now I want the number of molecules, right? So how can I get the number of molecules? Avogadro's number. In 1 mole of anything, there's 6.022 times 10 to the 23rd. So what did I do? I converted grams of water using its molar mass of 18.02 to moles. Those units cancel. And then in 1 mole of anything, there's 6.022 times 10 to the 23rd. Now here's the beautiful thing. This question asks how many molecules of H2O and 3.64 grams. It could have asked, instead of this, how many hydrogen atoms in 3.64 grams. So we would have done the same thing we did here, but we would have had to ask an extra step. In 1 molecule of H2O, there's 2 hydrogen atoms. So I would just take this number and multiply by 2. So it's very powerful. It not only can count the number of molecules, but the number of atoms given a certain weight. So here's an example that, if you want, you can pause this and work on it. I'm going to work through it because the videos get kind of long. But if I have a sample of molecular bromine, why molecular bromine? Bromine's an element. Why do they say molecular? That's because of it being a diatomic, Brinkelhoff, right? That little trick I talked about. So you want to make sure when you calculate molar mass that you're going to use Br2, because even though bromine's an element, it's diatomic. So the question is saying, right, if I have 2,100 grams, how many molecular bromine molecules are there? So I'm going to go same route, grams to moles to number of molecules, just like I did earlier. How? Molar mass, Avogadro's number. So there's the molar mass of bromine, and you got to make sure you use the correct molar mass because it's a diatomic. And then there's Avogadro's number in the second conversion factor. And again, what could I do? I can convert this to bromine atoms instead. I could say in, 1 molecule of Br2, the diatomic element, there's 2 bromine atoms. This problem didn't ask that, but I'm showing you, you have that flexibility. So when we're looking at formulas, realize that we can always scale these ratios up, and this is going to be very important for the next couple of videos you'll be watching. So in chemistry, when we look at ratios like H2O, I don't want you to think, oh, there's 1 molecule of water and there's 1 atom of oxygen and 2 hydrogen atoms. No, I want you to think there's 1 mole of water and there's 2, this subscript 2 moles of hydrogen atoms and 1 mole of oxygen atoms. I want you to scale everything up because everything's in terms of moles because that's a meaningful size. So there you go, 2 moles of hydrogen atom. So if I had carbon tetrachloride, why is this carbon tetrachloride? It is a binary covalent compound. How do I know that? Both carbon and chlorine are nonmetals, so I have to use the prefix tetra to show 4. But in 1 mole of it, I have 4 moles of chlorine. How come? Well, the black circle represents the carbon and the green circles are chlorines. So 1 mole of this would give me 4 moles of that. And I can use that as a conversion factor. So let's look at barium nitrate. What are all the mole relationships? Well, what do you have to do? Barium, right? Group 2A. Nitrate, another non-metal 8. So there's nitrogen, The oxygen's not on the 4, so there's 3. I have to do my crisscross applesauce, and I get my barium nitrate formula. And now I can look at the subscripts and determine actual mole relationships, which are more meaningful. Right, so there's the formula unit. In 1 mole of barium nitrate, there's 1 mole of barium. In 1 mole of barium nitrate, there's 2 moles of nitrogen. How come? That subscript 2 means there's 2 of these nitrates. And each nitrate has 1 nitrogen. And then there's 6 moles of oxygen, because each nitrate has 3 and there's 2 of them. So a chemical formula gives the relationships between moles, but not grams. It's a mole relationship. The reason why it doesn't do grams is because each atom has a different molar mass. Okay. So we can always convert to moles and then use a mole relationship to get what we need. So can we determine the number of moles of oxygen in 2.45 moles of nickel 2 phosphate? So nickel 2 phosphate, right? PO43 minus, you're going to crisscross. So again, I crisscross. So I have 2.45 moles of this. How many moles of oxygen? Well, there's 8 moles of oxygen per 1 mole of nickel 2 phosphate. So I take 2.45 and multiply it by 8. I get the number of moles of oxygen. Very powerful. So moles are just ratios. And we use a periodic table to determine the molar mass of something. And we also understand that whenever we have 1 mole of anything, that represents the number 6.022 times 10 to the 23rd, because a mole just represents a number of particles, just like a dozen represents 12. I hope this makes sense. I hope this was a useful video, and thanks for watching.